Welcome back. Today we'll be looking at Assignment 8, Section 3.2, which talks about the ideas of differentiability. And recall the definition of what it means for a function to be differentiable at a point x equals a. What must be true is that the limit as h goes to 0 of f of a plus h minus f of a all over h, that limit must exist. And so that asks the question, or at least begs the question, what does a function look like if it is not differentiable? So here are a couple of pictures of functions which are not differentiable at a point. A typical absolute value type function is not differentiable. A function that looks like that, its equation might be something like x to the 2/3. So here we have a corner. And this function is not differentiable because the tangent line does not exist. We have a different expression for the tangent line depending upon whether we come at this point here from the right or from the left. This cusp is not differentiable at the point because the tangent line is vertical, and since the tangent line is vertical, the slope of the tangent line does not exist, and so the slope does not exist, and therefore the function is not differentiable. There are two more classic types of functions which are not differentiable. I'll draw this one like this. That might be something like x to the 1/3, and it's not differentiable at the point right there because we have, again, a vertical tangent. And since we have a vertical tangent, the slope is undefined. The derivative is the slope of the tangent line, and there is no slope of that tangent. And finally, the last one would be a function which perhaps looks like this, which you'll remember is called a jump discontinuity. And the reason that this function is not differentiable is because there is no tangent line at the point of discontinuity. The following is a pretty important idea about what it means to be locally linear, or to exhibit local linearity. And the idea is this, that if a function is differentiable at a point where x is equal to c, then if we were to zoom in farther and farther on the graph at the point where x is equal to c, the function would begin to resemble a straight line. And indeed, that straight line would be the tangent line to the curve at x equals c. This is something that's very easy to do with your graphing calculator, and I encourage you to take any differentiable curve that's smooth and without any corners, and zoom in a bunch of times at any particular point, and you'll notice that the graph begins to resemble a straight line. So I suggest you do that before you move on. So here's another one of these big ideas regarding differentiability and continuity. And as we state up top, if a function is differentiable at a point A, then the function must be continuous at that point A. And remember, again, that if a function is differentiable, that means that this limit exists. So why does that limit existing mean that the function has to be continuous? If you remember, there's three parts to being continuous. F of a must exist. Well, this limit can only exist if f of a exists. The second part is that limit as x approaches a of f of x must exist. Well, if you look at this part of it, there's no way that this limit can exist if this little piece doesn't exist. And finally, and the most interesting one, is that a function is continuous at a point A if the limit as x approaches a of f of x equals f of a. Now notice, as x goes to a, the bottom goes to 0. And there's only one way that the limit of a quotient can exist if the bottom goes to 0, And that would be if the top goes to 0, which means f of x must go to f of a as a limit. So that's a quick little description of why it must be true that if a function is differentiable at a point, it must be continuous at a point. But please understand, very simply, that the converse is not true. And it's very easy to see that. The easiest function to help you see that would be an absolute value function. And it's very simple to see that this function, yes, is continuous. It's continuous everywhere. In particular, it's continuous at 0. But this function is not differentiable at 0, because if we come at it from the right, we get one limit for a tangent line, and as we come at it from the left, we get a different one, and so there is no tangent line at x equals 0. And finally, to finish up this lecture on differentiability, we are reminded or told about the definition, the theorem, intermediate value theorem for derivatives. Now remember that a derivative of a function is a function itself. So this is really a restatement of the simple intermediate value theorem for any function. And all it says is that if a and b are any 2 points in an interval over which f is differentiable, in other words, the derivative exists, then the derivative will take on all values between f of a and f of b. It's a pretty simply stated theorem that will be of importance later on when we're looking at antiderivatives and integration. So that concludes today's lecture. See you next time.